Okay, hi everyone. Good to see you here. I'm sorry if my voice is not as strong as usual, but I hope the meaning will still pass through. I'd like to start with a note about the exercises that you're getting. I know they're kind of different what you might be used from different courses or things for undergraduates. We're not expecting you necessarily to get to a concrete, the correct answer. There could be many correct answers. We mostly want to develop your ability to handle such questions and to show creativity, to show perseverance, to show numerical thinking, and to improve these proficiencies. And if you're able to achieve that, we're super happy. And also the grading that we're doing is along those lines. It's basically, if we see you did it properly, you did an effort, that's great. If we see that, you really did not invest in that, we'll probably be sending you an email or expect you to do more. And if you're doing superbly well, we'll mention that, and we'll also mention it to ourselves and usually give you a bonus at the end of the year. So that's how it works in terms of grading. Okay. Something else relates to the issue of using numbers. When you're putting numbers, and obviously that's the essence of what we're doing in this course, we have kind of like a no rumors policy. What does that mean? It means that you could either have you could use a number. It could be either based on the fact that you have a reference, that it could be something online, it could be a paper, it could be Wikipedia, that's fine. Or it could be based on your gut feeling, your intuition, that's also fine. But then mention, my intuition is that, my gut feeling is that this is the number. Otherwise, you're just putting something and we don't know where it came from, either from this or from that, both are fine. Just be sure to note. And obviously, there's a difference between those, but we accept both. But for you, it's important you'll be aware of it. Okay, so I want to start with something that also relates to how we're playing with numbers very often. That's the issue of significant digits. So let's, just to give a concrete example of, how does that arise as something. Let's say, somebody tells me that he'll be calling me in 5 minutes. Okay, probably happened to you quite a lot. What sometimes happens, that's more rare, I made it for this example, is like, let's say 10 seconds later, somebody is coming to me and saying, when will he call you? So what should be the right answer? In 4 minutes and 50 seconds, right? And that's like the accurate calculation. 5 minutes, he said, I'll call you in 5 minutes, 10 seconds passed, so he'll call me in 4 minutes. I probably wouldn't be saying it that way, right? And probably you wouldn't either. So why wouldn't you say it that way? Even if it was, half a minute later, you wouldn't say he'll call me in 4 minutes and 30 seconds or 4 minutes and a half. Because, there's something in the way that we state numbers. We also know something about what's the uncertainty associated with it. And the way we talk about it or write it, you often, I wouldn't usually say he'll call me in 5 minutes plus minus 2, right? Even though that's kind of like what you want to know, like something about the uncertainty. But we don't do it. Not only don't we do it when we talk with people, we often don't even do it when when we're doing, say, biology. In physics, they don't usually allow you not to do it. But in biology, usually, like most numbers that you see reported or analyzed, you don't give the uncertainty very often, which might be a bad thing, but we're not here to solve all the problems of the world. I just want to convey the sense that in the way you write the number, it means also something about the uncertainty. And in that sense, the uncertainty I have about those 5 minutes is like plus minus a few minutes. And therefore, even after a minute, I would still say in 5 minutes. And then you could say maybe after 3 minutes, I'll say he's supposed to call me very soon, in a minute or two, or whatever. Okay, so that's an example of significant digits. We could take another example. Let's say you're measuring the volume of cells. Okay, and you measured several cells. Let's say you took, some mammalian cells, and you measured 3 cells. Okay, and the combined volume is, let's say, 5,000 micrometer cubed. Okay, and now in the paper you want to report now to whoever you're talking with, not the volume of the 3 cells. You want to report the volume of the cell. So what will be the volume that you'll be reporting for the cell? So what? Give me some options. You don't have to stand behind the number that you say. Just suggest some options. So a third is fine, but I don't, you don't usually write it as a third of something. Yeah. 2,000. Okay, so one option is 2,000. Another option? How much? 1,300. Oh, maybe 1,600. It's a bit confusing. I think you will think if it's 4,000. 1,666. 1,000. Okay, so I'll say, I would generally buy all of them. What I first of all want to make sure, I didn't do like an empirical study about it, but actually you'll find that in many cases, people will report it as something like that. Sometimes a bit more digits, depends on if you did it in Excel, that's the answer they give you, and you just plug it in. And I think it's clear why this is not the uncertainty associated with these things. Doesn't matter what you measure with, and even just by the fact that it's 5,000, I'm telling you that we're giving the rough number. I didn't give you exactly. It would be very rare occasion that's exactly what came out of the machine, 5,000. And now if you ask me, all answers are correct. This also seems a bit too much. So, if you want to look very accurate, you can put this, although I would often say that this is the more right way to convey it, given the uncertainties. Okay, so now you can tell me, it becomes kind of like an art. How do you choose? Well, it really relates to if you know the uncertainty, but usually don't know the uncertainty, usually have the uncertainty somehow in your intuition or something like that. So let me give you a simple rule. In almost anything you'll do in this course, it would be the right thing to do to choose just one significant digit. Okay? By the way, this one, starting with 1 is order of magnitude. That's half a significant digit if you want, just giving the order of magnitude. But one significant digit is usually fine. Sometimes if you have a good reason, you might be using 2 significant digits. And that's probably usually also true for the paper. We're publishing several papers in pretty good journals. Usually it's enough to use 1 or 2. When you're using more, you seem sophisticated, but you usually just, you're just not being very good in how, very hygienic in how you use numbers. Sounds okay? Anybody has any concerns about it? Because I do have a concern. Let's say, for example, so, with these rules, you also think, sometimes there's other things that happen. Let's say I wanted to know the number of, no, let's write it differently. What is the annual increase in the population of Israel? Question is clear? I want to know, between, let's say, 2023 and 2022, or what would be 2024, what would be the increase in the population of Israel? Humans. I don't know what you were hinting at, but let's stay with humans for now. Okay, so one way to do it is to say, okay, what's the population of Israel today? Yeah, so I think it's about 9 million. It's true, everything is 10 for us, so we could make it 10 million, but it's about 9 million. What was it last year?
9 million.
Also about 9 million, yeah. And now when I'll take the difference, I'll get nothing, right? So not so great. Maybe there are some countries in which the population is relatively stable. But Israel is not such a case. It's kind of an outlier in that respect. Okay, so I should do it more properly. So I don't remember exactly the number, but I think it's something like 9.6 million. And then it was the year before, it was about 9.5 million. And then you get about 1.1 million. And that would be about right. Okay, so the population of Israel increased by about 100,000. But you can see that also this, if I'm unlucky in some, and I'm rounding to the, rounding this way or that way, I could easily get 0 or 0.2, and that's much more of the uncertainty that exists. I could do much better. So in this,
very much depends on the circumstance within that year. So I suppose you need a longer time frame to actually infer something.
yeah, okay, that's an interesting point. The question is, whether it's fine to do it just by taking 2023, 2022, and just subtracting that versus it's true that you could, you can do it with more years and do it more accurately. My guess is that it's pretty consistent through the years because I don't think there's any reason why, people do more babies, 1 year versus the other. There are some such cases, like say, World War or something like that, but that would never happen in Israel. So I don't think it's relevant. Okay, so in this, putting that aside for a second, so, you could probably do it like 9.62 and then 9.53, and then you do the difference and it's 0.09, and then it becomes even better in a way. And probably I could choose if I want to report it as this way or to just say that's equal to about 0.1 million. But this is a sort of case that's different than using one significant digit, not good enough. Two significant digits, so you need more. And that's because I'm taking the difference of numbers that are pretty close to each other. And also the accuracy of reporting them is known pretty well. Like people know the population of a country usually pretty well. Or at least even if they have a mistake, it's usually what's known as a systematic mistake. Meaning maybe they're underestimating it. It might be that, the Bureau of Statistics is underestimating by 100,000 people, 200,000 people. But it's the same underestimate by 200,000 people in the year 2023 and the year 2022, and therefore when you're taking the difference, the annual increase is roughly correct. Okay, that's a different point about the difference between systematic errors and whatever is the name for the other type of errors. But that's a different subject. Good. Any comments about that? So we're making a lot of progress here. We talked about this and that and this and that. We didn't talk about this so much. Okay.
I want to ask you about the hygiene point when you say more significant. The point is to be more hygienic. But you have all sorts of intermediate values when you're trying to calculate essentially you get from point A to point B. So all the numbers that you get in between, if you round them too much, that it compounds and leads to
yeah, you're right. Yeah, so what's your name? Eli. Okay, so Eli has a good point that I didn't get into, but it's great that you mentioned that. So what happens when you have a calculation with several steps? Then it's true that the hygienic way or the right way to do it is actually to use more significant digits there, also depending on the uncertainty, but because we don't always know the uncertainty, it's fine to err to the direction of using more significant digits. Let's say 2, maybe 3. If you're going to take the difference, you might need more. I know in the intermediate steps. And then when you get the end result, then consider how you want to report it. And I'm saying usually 1 or 2 significant digits is the right way to do it. But along the way, maybe it's also as not to compound errors, especially if you're going to have things like differences or something like that. Okay. But don't give us also like 6 digits after the decimal point or something like that. That just looks funny. Okay. Good. So you might remember that I guess it was in the last lecture that we were asking the following question. How many H plus ions are in a bacterial cell? Okay, we were thinking about something like, say, an E. coli, for whom you know the volume, etc. And we're asking how many, if I was counting all the H plus, so often they're hydrated, so it's nicely, it's usually in the form of H3, H3O plus, and the bacteria I'm taking to be E. coli. And to make it interesting, I'm also giving options. A, it was like 10 to the second. B was 10 to the 4. C was 10 to the 6. D was 10 to the 8. Just for my enjoyment, let's do a vote once again. So who's voting for A, 10 to the second? 1. Who's voting 10 to the 0? Who's voting for 10 to the 4? A few. Who's voting for 10 to the 6? Okay, the majority of the class. Who's voting for 10 to the 8? Also quite a few. Okay, so it's very, I would say people voting here by far. So allow me the freedom to, to keep you in suspension for just a bit longer. In order to be able to answer it, let me help you with answering something more general. And then it will be easy to utilize it for this. So the subject today is concentrations and absolute numbers. So let's try to connect these two threads of concentration and absolute numbers. And I promise it would be useful. Also, beyond the class, I find it useful a lot. And in order to that, you need a rule of thumb, okay, to do it in biology. And the rule of thumb should go as follows. What is the concentration of one molecule in a bacterial cell volume? Okay, as you see, I don't like to give answers. I usually like to give questions. I think that, that's a better way to learn. And when I was giving the quote concentration, so you understand, like I'm talking about, let's say, bacterial cell, an E. coli, and let's say I have one molecule there. What is the effective concentration? Obviously, in the end, usually you don't talk about one, so it would be like 1,000,000. But then if I get an answer for one, I could just multiply and get the 1,000,000. Okay, and therefore it's good to work with one, and then you could afterwards convert it to whatever you want. The concentration, the question is clear? Okay, so let's do a quick vote on that. Is it 1 picomolar, 1 nanomolar, 1 micromolar, 1 millimolar? Question is clear? What's below picomolar? Anybody knows? Femto. So let's add it here. Femtomolar. Okay, I think for now, instead of doing another vote, let's just do some other thing. What can we do if not a vote? Yeah, let's do a calculation. But I'll be happy if before I do it, you try to do it, let's say in pairs or something. Or each one, and then you talk with the person next to you to try and get there. Let's take 5 minutes and try to, play with it. And, get as far as you can. I'm not expecting everybody would get to the end. Just try to make some progress or to see what's missing for you. And then when I'll do it, you'll know how you could have solved what was missing. Okay, you can also break down the question into steps and get as far as you can. Okay, clear? Good. Okay, I suggest we continue, even though I have to say that this combination of seeing you work and listening to Alon Eder is something I can continue for a long time. I'm really enjoying myself. But let's also try to answer this. So I saw different ways of approaching it. I like to take something. I'm looking for usually for methods that are very robust, like that. That I know that I won't make mistakes, and that I could always use like a similar thing when I'm dealing with different problems. Okay, so I want to look at the input the data that I have. What do I know? I know that my concentration is equal to 1 molecule per 1 cell volume. Okay, that's not too difficult. It's just stating the question as an equation. Strange equation, but still something you can work with. And from here onward, I'll be using, if you want, like a tool or a trick that I'm always allowed to do, and that is multiply by 1. Okay, I'll multiply by my way by 1 until I get the answer that I want. Where the answer that I want would be somewhere here. It's supposed to be molar in terms of units. Okay, my problem is that this is not in the units that I'm interested in. It's not molar. Okay, anybody remembers what's the definition of a molar? Mole per liter, right? Okay, good. So now my only problem in life is that I'm in molecules and I want to get to moles, and I'm with cell volume, I want to get to liter. Okay, so let's start multiplying by 1. So for example, I want to get rid of the cell volume. So I can again multiply by 1. What would I can say 1 cell volume is equal to, so what is the cell volume? I remember my cell is like a micron in length scale. Okay, so it's a micron by a micron by a micron. Okay, so it's 1 cell volume is 1 micrometer cubed. Okay, you see I multiplied by 1. The nice thing is that the units here are equal. So now I can say, I'm doing it the long way. I know some of you can do it more faster, but allow me to do it step by step. So this is going to fall with this. And now I have 1 molecule per 1 micrometer cubed. Okay. Let's multiply again by 1. What multiplication by 1 would I do now? Let's say I want to get rid of the 1 micrometer cubed because I want to get to liters. So 1 micrometer cubed, how many liters is that? So I don't know, I'm getting confused with these things. 15, 18, 21, what's happening there? I don't know. But I know that micron, I do remember, it's 10 to the minus 6. And therefore, it's easy for me to say this is like 10 to the minus 18 meters cubed. Okay, because multiplying 6 by 3, that's something I know how to do well. It's 18. Okay, and that's again nice because now I'm going to get rid of this. But that's not good enough. I'm in meters cubed, and I want to get in the end to liters. So what would I do? I would multiply by 1 once again. I want to get meter cubed, 1 meter cubed. And now I want it to be liters. And that I remember, that's 1,000 liters in the meter cube. I'm going to run into space problems, but not to worry, it will be okay. Okay, so now you see that I got rid of this again. Meter cubed and meter cubed. No, something. Yeah, sorry, yeah. It's okay. So far, I could completely. What I wanted is not to delete the value. I'm just deleting the units. Okay, the units are going to cancel. The values stay okay. Until now, it was 1, so nothing to worry about. But here, I don't want to cancel the minus 18. Okay, thanks for explaining to me what I'm doing. Okay, so it's just this. Okay, now we have the liters. Now I have the issue with the molecules versus moles. Right, so let's multiply again by 1. How do I do this? I want to get rid of the molecule, so I want to have one molecule here. And I want to have something with the numbers of molecules. Yeah. Or you know what? Let's do it even more nicely. You could say, I don't even remember, like how to do the minus. Let's just say one Avogadro number. Yeah, 1 mole. And then what would be the number here? How many molecules? 6 something. We said 10 to the 24. Instead of 6, 10 to the 23, we just, order of magnitude is 10 to the 24. And you can say this was, again, what was important, it's important the units, I want to multiplying by 1, right? This is equal to this. I want to get to molecules to get rid of the molecules. And I could have done it 1 molecule, 10 to the minus 24 mole, but that's a bit less intuitive. Am I correct? Am I mistaken? Whereas just 1 mole and 10 to the 24, no way to get it wrong. Okay, and now I think now we're ready. Why am I ready? Because the molecule in terms of units would fall with the molecule, and I'm just left with moles per liter. And now I just need to see what I have. 1, 1, 1, 1, 1. Okay, that's easy. I have 1 molar divided by 1, 1, minus 18 plus 3 plus 24. What is it? Liters. Okay? Good. I hope I'm not mistaken because I can't follow on this by head. Okay, so this is minus 18 plus 3, minus 15. Minus 15 plus 24, 9. Good. 1 molar in 10 to the 9 liters. That's equal to 10 to the minus molar in 1 liter. Yes, small, sorry. So the mistake was here. Which is 1 nanomolar. We did it right. Okay, but usually it doesn't take that much energy. And the important thing is that every step here is like close to trivial. And with experience, you might do 2 such things together, 3 such things together. But the important thing is it's pretty robust in terms of like there was nothing. I didn't to have any imagination, special imagination here. And that's a useful way to do things. The sweet thing is that now, for many other things, you can now try to apply this once you have this rule of thumb. Anybody has a suggestion of how they might apply it for something else? What? Yeah, concentration of a drug or anything else. Yeah. Anybody measuring something in the lab that they could use it for? So usually if you have, now you could also use it in the other way around. Like if you have a concentration of something, you can infer what's the number of molecules that you have. Okay, so I think, try to keep it in your hand next time you do an experiment and you have a concentration, and you can now easily convert into an absolute number. We might still be doing such things, but for a second, I want to spend a minute or more on this small n, the nano. Okay, let's talk about nanos for a second. There's nano chemistry, lots of things in nano these days. So nano is 10 to the minus 9, right? So this 10 to the 9 is something that I'm curious to improve our intuition about. Okay, like it's a billion, right? 10 to the 9. it's something that appears in many, value of money and this and that, number of people. So it's good to build our intuition because we're going to use that in different things. And for that, let's take a concrete example that I want you to help me with to develop our intuition. Let's say I'm doing the following experiment. I'm standing at the equator and I'm putting a ball, let's say a green ball of, I don't know, what do you like more, golf or ping pong? Who's voting for ping pong? Who's voting for golf? Okay, in Israeli audience, I think it's more like ping pong. Okay, so you're putting a green ball of ping pong and then you're starting to put normal ping pong balls, which are usually white, right? So you just, you're standing at the equator, you put, now you're putting white one, another white one, you're putting 1 billion white ping pong balls, and then again you're putting a green ping pong balls, and then another 1 billion white ones, and then a green one, and 1 billion, until what? Until you reach back where you started, somewhere in Kenya or whatever. You went through the whole. And my question to you is, how many green ping pong balls would you put by the time that you get back to the beginning? Question is clear? Okay, so now what we'll do, we'll take a recess, and in that time, I would be happy if you try to come up with a number. Okay, so 10 minutes recess, spend it with ping pong balls and anything else you need. Okay, we're back to the world of ping pong. Anybody want to throw in what they arrived at? 4. Okay. Anything else? 1.
I got 1, but we're having an argument.
You're having an argument. Okay, good.
Depends what diameter of your ball.
So how do we approach this? Anybody wants to say how they came about? Yeah.
Okay, so first we calculated for Google the circumference of Earth.
Okay, circumference of the Earth.
Yeah.
Okay, what did you take for that?
And so 40,000 kilometers.
40,000 kilometers. Why?
Google said.
Google said. Okay. Anybody has a different way to do it other than Google said? Like, okay, what's the radius?
6,000. Do you know the radius? Same thing, basically. We just added another state calculator. You can take a stick and put it in the ground. Look at the shadow.
Okay, so we had the Google set for the 40,000. We had the approach of 6,000 kilometers, the radius. And we remember there was some smart guy in Egypt or Greece or something like that. You can put a stick and look at somewhere else and see how much shadow and what's the difference in the well, something like that. Okay, so we have like a spectrum of options of how to approach it. The Google is fine. I would say that like in 2023 or 2024 now, we have the problem that if we only depend on something from the web, we're not always sure whether it's correct or not. And and it seems like it's just going to get more complicated in years to come with fake proof, not for Google but for other things. What are the sources? ChatGPT gives you something, etc. And actually, the sort of thing that we're doing in the course, I think, would help a lot. And for that, it's good if you carry some numbers in your head. Either you take them from Google at some point, from somewhere you believe, or like knowing the radius of the Earth, given that you're going to stay living here for a long time, I think it's fine that you'll carry that in your head. And 6,000 kilometers, that's about right. And then from 6,000 kilometers, how do you get to 40,000? Yeah, so you can do something with 2 pi, or you can just say, okay, it makes sense, 6, and then there's like another 6 here and 6 like that. It would come out to about right. Or 40,000. In the end, I don't even care if it's 30,000 or 40,000 or something like that.
Can you demonstrate how to do that?
Yeah, like it's supposed to be the radius, but let's say instead of the radius, I'm just saying from where, let's say I'm standing here, to the pole, it would be also kind of like 6,000, and then again 6,000 from the other side, and then to the other pole, and then so 4 times 6,000. not so.
That's if you go into space, not if you go on a curve.
Right. So I remember there's something with geometry that like it's like this and not like this. Okay, it's like a factor of 2. I don't care so much factor of 2, but it's about right. Okay, it's good. Okay, so we have 40,000 kilometers. What did you do next?
So then we estimated the diameter of a ping pong ball, which he said is about 4 centimeters.
Okay, great choice. Why 4? How do you estimate it's 4, not 3?
Random.
Okay, so it's hard to estimate, but actually it's fine that you'll make your life easy. Life is complicated anyway, so we could make our life easy when we can. We know that you had 40,000 kilometers, so you're saying let's take 4 centimeters for the golf ball, for the ping pong. The diameter. Okay, good.
Then we converted both to meters just to make it easier, but I guess we could also just convert the centimeters to kilometers.
Okay, no, so you converted this, so you got what? This is 4 times 10 to the 4.
Yeah, times 10 to the 3.
By the way, note that if you want to know, it's like 10 to the 3 meter divided by 1 kilometer. It's like, again, if you want, it's like the example we did before, you're multiplying by 1. Okay, of course you can do it in your head, but just to show how it's general. Okay, so 4 10 to the 7 meters. And you did the same thing here, right? 4 times 10 to the minus 2 meters.
Exactly.
And then you divided both of them.
Yeah.
And lo and behold, when you divide these two, 4 times 10 to the 7 by 4 times 10 to the minus 2, you're getting 10 to the 9. Which means that once like a billion balls would be enough, even though the small one, ping pong balls, when you're putting a billion, you go through the whole Earth with all the oceans and continents and everything like never in life will be able to do. A billion balls could do it no problem. Why did I give you that example? Why did we do this?
Maybe because it seems a billion seems too little.
Yeah,
Or
because
you don't know how much.
because like we know the world is like gigantic, and balls, well, we know balls, and a billion also like it's a big deal, but now we're spending every day $1 billion shekels or dollars or something, or this or that. So it doesn't seem like that could solve the problem of going through the whole world. But this relates to the fact that our intuition with big numbers as well as with small numbers is usually not that great. And for that we need calculations and to improve our intuition. So I guess now you understand better that a billion could be like really a lot. And also that like you do the calculation and you improve your understanding, and then the world is big, but to an extent. It's not infinite. Just a billion. That's at least in linear dimension. If we're doing it 2-dimension or 3-dimension, numbers would need to be bigger. Okay, so this was and if you were surprised by that, that's great, because that was exactly my intention. By the way, you're welcome to ask, it's a good icebreaker, when you want to try to teach something or, like do something with people, it's a good way if that's the kind of things you like. Okay.
By the way, if you're speaking to somebody from England who's older than 50, then a billion used to be a million.
Yeah, okay, so a good point by Yossi, that like maybe you'll run into that problem if you read something old or like you talk, that like a billion is also crazily could mean different things, different numbers to different people. Not by a lot, just by a factor of 1,000. Okay, like it used to be that like a billion was also known as a trillion in some places of the UK and stuff like that. Okay, but that goes back to this thing with the nanomolar. That nanomolar is like nano is 1 in a billion. So you understand this 1 in a billion is also something pretty crazy. It's like one such green ping pong ball out of all the ping pong balls that are going throughout all the Earth. Or one molecule out of all of those molecules. So we should pay respect to a nano. Okay, so with that, let's go back to our rule of thumb that we had here. Let's see if we could apply it to other stuff. So let's say I was asking the same question, but now in a mammalian cell. Okay, we have one molecule, like what is the concentration of one molecule in a volume of a mammalian cell? So let's see how easy it is. Let's see, we had before, what was it? Femtomolar, picomolar, nanomolar, micromolar, millimolar. Who's voting for the femtomolar? Who's voting for the picomolar? For the nanomolar? For the micromolar? For the millimolar? Okay, so I was asking pretty quickly because I wanted to get a, and it could be confusing sometimes, right? Like, is it, like, should we go this way or that way? Did something change or not? Usually in concentration, things do not change. So what's happening here? Like, usually when you have a concentration, it's independent of the volume.
You keep it one molecule.
But you keep it one molecule, right? And then should I go up or down from the nanomolar? Yeah, so I'm using now a bigger volume. How much bigger? So usually, like, am I thinking about the mammalian cells? It's usually about 10 times in every dimension. Okay, instead of like 1 micron, it's usually like 10 microns. Instead of 1 micrometer cubed, it's 10 by 10 by 10, 1,000 micrometer cubed. So 1,000 times more. And I'm still throwing in just one molecule. So the volume is 1,000 times smaller. Okay, and therefore I'm going from nanomolar to picomolar. The nice thing is you didn't have to calculate it again. Okay, like if you had the rule of thumb, it's easy to go from bacterial to jump to mammalian. So, like, just show again, like, things it could be used for. So, in this building is one of the most famous, if not the most famous, protein associated with cancer was studied for many years in several labs. It's called P53. Anybody heard about that from biology? Yeah. It's like, they teach it, until you're tired. And so I came once to, one of the professors who basically the whole career was based on studying that protein. And I was asking, how many copies are of this protein in the cell? What do you think was the answer?
It depends.
Exactly. So it depends, which, is a great answer because nobody could say you're wrong. But I said, yeah, I know it depends, but just, roughly, is it like 1,000 copies, 1,000,000 copies, 1,000,000,000 copies, 1,000,000,000,000 copies? And I did not get an answer, even though it's like something, has been studied for, like 30 years. That's like, the whole career, and which is interesting, right? What is the answer, do you think? 1,000, 100? Let's try to estimate it. How would we estimate it? Anybody remember something that we did, I guess in the first lecture, about the number of proteins in a cell? So what was it? Yeah, a few millions, somewhere between 10 to the 6, 10 to the 7 per cell. Okay. So let's see if that could help us. We had in a bacterial cell, we had 10 to the 6 to 10 to the 7 proteins per cell. Okay. Let's say this P53 is just like another normal protein in the cell. How do we go from here to there? And to the concentration, number, absolute number, yeah.
Maybe you know how many protein encoding genes you have, and you can divide this by the amount, like 22,000.
Okay, so the suggestion is to go, so this was bacterial cell. So we need to do two steps. One is to go from bacterial cell to a mammalian cell, and the other to go from all of the proteins to a single protein. And you're saying there's like some number of genes coding for proteins in a cell. Sounds fair? Okay, let's do it quickly. So if we had, this is per bacterial cell, so if we want to go to mammalian cell, what would that be? Factor of 1,000, just like we talked before. It would be 10 to the 9 to 10 to the 10 proteins per although I would say, there's variation in mammalian cells. So here we're talking about some characteristic mammalian cells, so like 10 micron by 10 micron, that's 1,000 micrometers cubed. Maybe if it was a big neuron or some muscle cells, it could be quite different, or red blood cells, which is pretty tiny, but order of magnitude reasonable. Okay, this is total number of how many proteins are in a cell, like different kinds. Related to how many genes we have.
24,000 for humans.
Okay, so 24,000 is the number that comes to mind.
Yeah, but if you consider the alternative splicing and everything,
Yeah, okay, but then there's different splicing. Okay, so you see, biologists were really good at complicating things. But I'm just trying to get an order of magnitude. So I'm fine with just saying, let's say there's 10 to the 4 different proteins. And from that I can infer, I need to divide this by the number if it's like a characteristic one. So it's somewhere between 10 to the 5 to 10 to the 6 copies per cell.
That's if you assume that they're equally distributed, but if you consider that there's a small fraction of proteins that are housekeeping genes, and they take up the largest fraction of the proteins in the cell.
Good. So the comment is that I was assuming it's like homogeneous, it's like the same for all the proteins. And the comment is that there are some things that are much higher abundance, and that's true. By the way, there's also many things that are at much lower abundance. And then I'm just kind of like assuming that P53, because it's being studied, then probably it's not one of the lowest. And because it's not a housekeeping, it's not something that, is like needed everywhere. It's like a transcription factor, whatever. It's not the highest. So I'm taking like an average. It's true, not a great assumption, but again, depending on what you want to get. I just want to get a rough value. Like I just want to be in a better position than this professor that's been studying it for 30 years and could not give me an order of magnitude. You could be stronger than them if you're willing to, take some assumptions. Just a second. So let's get to it. So I got just before. Let's first enjoy the answer, and then we talk about the caveats in the answers. Okay? Otherwise, we don't get to enjoy for a second. And also, or more worse than that, we sometimes don't even think about the answer. We just think about the problems. Let's just think about like what we got roughly. We got somewhere between 100,000 and 1 million copies. Okay? Sounds what? Too much. That's interesting. So your intuition is that it would be smaller. Okay, so so the intuition of some people here, this is like somewhere between 100 and 1,000 times too high. That's what I hear. Anybody has a different intuition? Everybody has the wrong intuition?
It depends on the cell type.
Why?
Because in some cells you have like
skipping genes.
Yeah,
Like
it's
a
true.
bone cell or
Yeah, it could vary. I don't think by 1,000 times. I'll be surprised if you have something 1,000 times lower. Is like between 100 and 1,000 copies. Try to find me a cell type like this. That's about 1,000, micrometer cube. So this is roughly the right order of magnitude. You can check many transcription factors. I was just taking P53, but you can take most transcription factors that you are being studied, that you've heard about, etc. You can find in my book, a table of such examples from the literature. These are the right orders of magnitude because they're not the most housekeeping, and they're not like not being expressed somewhere in the middle. That's roughly right. And seriously, now you know something about something very basic in biology, like these proteins being studied, that most professors do not know. And I think it's relevant. By the way, if I want to turn this into a concentration, what's the concentration of this transcription factor? Let's say 10 to the 6, just to make it easy. What's the concentration of P53 given this copy number in the mammalian cell? No, in mammalian cell, right? Okay, each one wants to take a second to try and take a minute. Try to think for yourself. If I know that I have 1,000,000 copies in the cell, now in a mammalian cell, what is the concentration? Okay, so it seems like you're making progress. So okay, so I'm trying to remember just one thing in life. Every time, like something as simple as possible. I remember this rule of thumb that we derived together. Bacterial cell, 1 nanomolar per molecule. Okay, and now it's a confusing question because there's two things that happened here, right? One is that I moved from a bacterial cell to mammalian cell. One is I moved from 1 to 10 to the 6. But there's more confusing things in life. Because the first step of moving to mammalian cell we already did, and we said we have to go like one step above. And it's like 3 orders of magnitude. So I went to a 3 orders of magnitude lower concentration, picomolar. And now I have 10 to the million, like 1,000,000 copies. So I'm going, this is 3 orders of magnitude, another 3 orders of magnitude. So I'm at 1 micromolar. And if you're interested, go and check some, protein that you care about. It's a transcription factor or something like that. I'm guessing it would be about a micromolar. And you can see I might be wrong, but I'm just telling you micromolar. I haven't told you 5 micromolar or whatever. It's like in the range of a micromolar, so it's within. I'm allowing myself 3 orders of magnitude mistake, above and beyond before I'll be really wrong. You see what I mean? Okay, and that's the kind of thing that you also can do the conversions when you have these rules of thumb. Okay, if you're so into it, or I am, how many water molecules are in an E. coli? Let's do it together. Question is clear? Ideas of how to approach it?
water.
70% water. You know what? Let's make it everything is water. Because 70%, 100%, I don't care so much. Yeah, so So anybody knows anything about, like, now, like we were doing everything on, like, I was giving you a rule of thumb to go from number of molecules to concentration. But I might as well use it in the other way around, right? If I have the concentration, to know the number of molecules. Anybody remember something about concentration of water?
55.
Yeah, okay, so those who are, have like memories from the undergrad, there's something with 55. Okay, what is this 55? The concentration of water in water. It's true. So that's like if you have pure water, what's the concentration of water in water? 55. What? Mol or molar. Yeah. Oh, so just as an aside, how did that come about? 55 molar concentration. Anybody has a suggestion how we could derive it quickly? Yeah, so what is the weight of water? 18, right? We have this 18, what is it? It's 18 grams per mole. Okay, because it's like 16 plus 1 plus 1. Okay, if you multiply these two things, what would come? 1,000. Okay, because there's 1,000 grams in a liter. Anyway, that might ring a bell, right? So we could derive it, but that's not what I'm interested in. I want to say, let's say you remember it, or you just need to derive it, or whatever. There's like about 50 molar of water in water. How do I go from this to the number of cells, to the number of molecules in a bacterial cell? Okay, so what's the number? How much does it arrive at? Let's make it just make it easy. Let's say it's 10 to the 2 molar. So how does this help me to answer this?
You can divide it by nanomolar and you just get the number.
Okay, which is?
I did 55, not 100, but I got 5.5, 10 to the power 10. So 50 billion.
Okay, so something around there. So we had the rule of thumb, right? 1 molecule, 1 nanomolar. So if 1 nanomolar is 1 molecule, how much is 1 mole? A billion, right? Because if 1 nanomolar is this, then 1 micromolar is 1,000, 1 millimolar is 1,000,000, 1 molar is 1,000,000,000, 10 to the 9. And I have 100 molar, so I have 100 billion, or 10 to the 11 H2O per bacterial cell. How many people are in the world? Okay, about 10 billion, so 10 to the 10. Okay, so 10 times more the number of people in the world. Okay, so finally, we could go to where we started. Because you remember I had a question in mind when we started all this. I wanted to know how many protons, free protons, ions are in a bacterial cell. And for that, I'd like to use what we have, what we just used. So, but there's a missing step here. What is the missing? How do we go from protons? I want to go to, in the end, I want to get to absolute number. And I did it through concentration. So there's this thing with pH. What's this thing with pH? What happens there?
Assuming the neutral pH, so the water is 10 to the -7 H plus 2 liter.
Good. So let's remind ourselves, pH is defined as minus log 10 of the concentration. Okay? And we remember something, that pH of a cell is roughly 7. So that means that if we write it that way, we could say in order to go from this, you could just do 10 to this, to the order of this. So 10 to the pH is equal to 10 to the minus pH is the concentration. Okay, I'm plugging in 7, I get 10 to the minus 7. What are the units? Molar. Okay, because actually this should have been, people don't usually write it, but it should be concentration divided by 1 molar. And that's because when you're taking a log, it has to be without units. But that's something nobody cares about except me, so don't worry about it. Okay, so we have 10 to the minus 7 molar. Anybody's willing to guess again about the answer to this question? So 10 to the minus 7 molar. How can we write it alternatively? Yeah, so because of the 10 to the 9th nanomolar, so it's 10 to the 2 nanomolars. And from 10 to the nanomolar, 10 to the 2 nanomolars, we can jump directly with our rule of thumb to this. Voila. We did quite a path, but but this is like, I wanted to show how you can now use it for different things. For example, here. So anybody wants to explain how they got it between 10,000 and a million times wrong? So know that there's our intuition again with numbers is not that great. Like with the transcription factor with the protein p53, we somehow thought it should be way lower. And here it's the reverse. We thought it should be much higher. Why?
Because it's not like the basic of energy, like all the mitochondria is doing, like create a gradient of H plus. That's all the basic 100 H plus in max to liter or gradient.
Yeah, so there's something really surprising here, because if you're taking a course in metabolism, maybe even in this lecture hall, not very recently, you see that it's a big player in cells all the time. H plus comes here, H plus goes there, you produce, you consume, you produce there's the chemiosmotic, thing about understanding how really the magic of life is based on those protons coming in and out, coming in and out. And therefore, it's surprising that you can do it with so few. Any understanding how come that this is that you can do so much with so few?
Any change will make a big difference. If you have a really large number, you can lots of it to make a difference.
Okay, so a small change could make a big difference.
Like it's really dynamic maybe in the cell, like even if you add one H plus, so it's not like this specific proton need to go all the way to the other side of the cell. It's like make interaction with water and another water molecule is releasing H plus in the other side.
Okay, so I think that's a very good point. The dynamics is very interesting and non-intuitive here. Like let's say if you need a proton, either you might have it here, or it might you can borrow it from here. Somebody consumes it from there. What happens exactly? There's all sorts of things. It could be very quick diffusion. It could be formation and annihilation of things. I could give some examples on that, but there's all sorts of interesting things in terms of dynamics here. There's also another thing, like what confuses me if there's 100, and I need to do millions of reactions. I'm not saying how many millions, but millions of reactions every minute. So if something is a bit out of balance, I'll be consuming all those 100 like this. And then there'll be nothing, and then the pH would go crazy. So how does that not happen? Anybody remember something about buffer? There's this word buffer.
Yeah.
So how does the buffer related here? So the cell also has a buffering capacity, meaning that you can use those 100, it would be producing new 100 for you. Okay, because like you have lots of molecules that are willing to emit those ions or uptake them if there's too many. So there's something they're doing kind of like homeostasis or balancing unless you really push it so that like it stays around 7 or whatever because of this buffering. So that's what, that helps our intuition understand, okay, why do you need buffering? Also how buffering enables you to work this way. But this thing with the dynamics is even more crazy. Let me give you one example and then we're wrapping it up and moving forward. There's the issue of the lifetime of a hydronium ion or hydroxyl. Anybody knows what's the lifetime? I didn't know that. Like if you have a water molecule, like it breaks down, how quickly does it, reforms with something else? So this is something it's hard to get intuition for those things. But the value, I found it somewhere, is 10 to the minus 12 seconds. The average lifetime. So now look at something interesting. If you live only 10 to the minus 12 seconds, let's say you only have one of these inside the cell. And now, the water molecules forms it, and then another water molecule. I'm trying to think of how it visits different places. How quickly does it visit different places? So if you have only one of them, and it lives 10 to the minus 12 seconds and reforms, it means that every water molecule, I don't have it anymore. You remember how many water molecules did we have?
100 billion.
Yeah, 100 billion, which is 10 to the 11 H2O per cell. So with 10 to the minus 12 seconds, if you're traveling in the world and only spending 10 to the minus 12 seconds in every location, you can visit a lot of places. For example, you can visit all the water molecules in the cell, all of them 10 times every second. So if you're, say, if you need to do some metabolic reaction and you have a water molecule next to you, and you need an ion, like a proton there, no problem. Just wait, very little and it's visiting there. You just have to catch it quickly enough. Okay? It's like super dynamic, apropos your comment before. And you don't have only one, you have 100. So that means it visits every water molecule 1,000 times a second. Okay. Crazy stuff. Yeah, you could see that like our intuition is not very good at these things because we're not usually spending 10 to the minus 12 seconds in visiting places. And therefore, our only hope in order to understand well the things that we study or that we want to study is to use numbers and clear logic in order to be able to handle that. Okay, I think there's much more in this to learn about what's happening with this. Just that I don't know enough about it. But I think if you're a good chemist, it seems like there's much more to understand here. Good. Okay, kind of the, getting close to the end of the lecture, I want to bring up this issue of like absolute numbers that we've been using here and try to ask why in general, why use absolute numbers? Like, why try to get to these units? Any thoughts? Yeah, less abstract. Like, as long as we were, we were with units of, pH of 7, whatever. And then even when we're saying, even if I tell you like it converts into 100 nanomolar, also it's a kind of like, you don't have any good intuition about nanomolars, so you're happy with nanomolars. Absolute numbers is something we have very strong feelings about. But it's not a mistake. It's like we have strong feelings because we usually have good intuition. Like, if I was saying something about the concentration of students in the class that it's in some crazy units, of your concentration, you might not care about it. If I'm telling you like 100 students, 10 students, a million, like you would know, million students can't be right in the class. But if it's within some strange units that you don't have an intuition for, with absolute units we have good intuition, or at least we have some intuition, and therefore we could also find that we're wrong and we're improving it. But that's something which is much stronger. Therefore, I urge you to often convert things also to absolute numbers. But there's a risk of what happens when there's like really big numbers or really small numbers, because for that also our intuition doesn't work very well with that. So how do we approach this? Last trick for today. And again, let's take a concrete example. How many ants are in the world? Now I know what you would usually do if I was asking this question. You wouldn't, you would go to your phone and try to Google it, right? Okay, let's do it. Google it. Let's see who's the fastest Googler in class. Okay. So we have an answer. 20 quadrillion. Okay, anybody else has an answer? Okay, seems to be a consensus from the people Googling it, 20 quadrillion. Okay, very useful. Now there's two questions about it, right? A, is it true? And B, what is quadrillion? Okay, so there's a number of zeros there.
Also, how did they estimate it? Like, they can't write down that.
Okay, so Erez says it's 15 zeros. Anybody thinks differently? Okay, so there's a cool thing that I've learned from somebody in class a few years back on how to know this, because I didn't know, like Erez, that it's 15 zeros. And it goes like this. There's million, billion, trillion, quadrillion, quintillion. Anybody see something interesting? Yeah, so it's something with Latin, right? Like 1, 2, 3, 4, 5. Okay, so it really, the name really gives you a good hint. And it's like in jumps of 1,000. Quintillion? Yeah, you're probably right. Yeah, my Latin is really bad. Or Greek or whatever. Okay, so unfortunately they're starting with like million being with 6 zeros. But then from here, 6, 9, 12, 15, just like was pointed out. Okay, good. So this is 20 times 10 to the 15 ants. Okay, but who knows if this is like a propaganda of somebody who wants to sell you ants or something like that, or something against ants, and to show you that, or maybe just in general, they just want to show off that like they have something with lots of zeros, and there's no way of knowing, like, is it right or not? What's happening here? Anybody? So it's an absolute number, but it's not a very intuitive absolute number that I could. And I'm looking very often to do a sanity check. Sanity checks are like, the best thing in life in terms of like being able to test things. So how do we do a sanity check on this? I like it. Ants per square area, maybe that on that I might have a better intuition, because as we showed with the golf balls, we don't have a good intuition on the whole world. But on that, I might be able to make some progress. Okay, so for that, what do I need to do? I need to divide the number of ants by the area of the world.
But you need not to like the water area doesn't have any mistakes.
Right, so I probably don't want to do it for the whole surface area of Earth. I just want to do it on the land area. That's what you're saying, right? Yeah. Although it's a factor of 3, so usually we could go ahead, but it's fine. Let's just do land area. So anybody knows what's the area of land area of Earth? Okay, we could Google it, but I could also do it like just how do I do it roughly in my head? I just think of something that I know. I like, like the US looks like this, and I remember the area of the US. Anybody remember the area of the US?
80 million.
Yeah, so it's like 10 million. 10 million square kilometers. 10 to the 7 kilometers squared. Okay? Yeah, no offense to Americans. But this is how it looks, and this is the area. Okay, and then I'm trying to think, order of magnitude, what's the land area of the world? Ten times that, right? Because this is the US, then there's Canada, which looks the same, China, which looks the same, Russia, which is a bit bigger, so, and then there's the other things. Altogether, it's about 10 to the 8 kilometers squared. Anybody Googled it already? What's the correct answer? Maybe they did the same way. How much?
500 million kilometers.
No, but the land area.
Yeah, I think.
That's the total area. The land. We talk about the land area.
50 million kilometers.
Yeah. So the correct answer is 150 or 1.5 times 10 to the 8 kilometers squared. Okay, so there's 15 US, not 10 US. It doesn't matter so much what we want to do. You know what? Let's make it 20 US, just so we'll be on the. So it would be easy with the 20 quadrillion, right? Because we said 20 10 to the 15 ants, and we make it 2 times 10 to the 8 kilometers squared. I don't have a good intuition for kilometers squared. What do I prefer? Meters squared, right? So I need to multiply it by 1,000. 1,000 in this direction, 1,000 in this direction, because it's kilometers squared. So I need to multiply by 10 to the 6 meters squared per kilometer squared. Again, I'm multiplying by 1. And therefore, I'm getting 2 times 10 to the 14 meters squared. That's the Earth. And now I have, this is 2 times 10 to the 16 ants divided by 2 times 10 to the 14 meters squared. And I'm getting about 10 to the 2 ants per meter squared. Watch out. So 100 ants per meter squared. What do you think? Okay, so some people are afraid, 100 here, it's a lot, but it seems like too much. But then other people are saying, they're crawling underneath and they're pretty small, etc.
Are they more concentrated? You can find like colonies with thousands of ants.
Right, and then there's a colony maybe with many thousands of ants on 1 square meter. Okay, so this is an example where you did a sanity check, and I would say that's considered sane. Okay, like if the number would have come, 1 billion ants per square meter, I would say, strange. Or if you get like 10 to the minus 3 ants per square meter, also strange, because there's lots of ants around. But this is like, we're not very good at like saying, like, is it 100 is like, it's somewhere reasonable. It's the kind of thing that the kind of sanity check you expect is to be within like plus, minus 1, 2 orders of magnitude, that would be fine. And therefore it passed the sanity check, and indeed, we think it's a reasonable number. Although if you want, you can read Yuval's paper, which gives a better estimates for different things, not just ants. But you can get what I hope you get from this is how by transforming from a value that's just in general into something that becomes more intuitive, absolute units per unit that you're aware of, you can check things. Okay, so I think we're kind of like done, except for leaving you with something for the next lecture. And so the teaser for the next lecture is the following, and I would also say you also have homework to do. So the new exercise is out today, and you have 2 weeks to finish it.
Can I ask a question about
Sure.
the sanity check? Sometimes things go against our intuition. So we're saying, like we're starting from our intuition, it's like around a cyclic argument. We're starting with our intuition, and then we're getting back to our intuition. But perhaps there are 1 million ants per square meter, and it's something not intuitive.
Okay, so if I understood correctly, what Yossi is saying and asking is like kind of like what happens if you did a sanity check and it came insane, and like you can't say that, it becomes a bit cyclic if you say, okay, that means that it's wrong because maybe you're wrong. So what I would say is that's a great example of like this is the sort of place where you need to check more, do research. Research it means that like something in your intuition is different than what Google said, what the lecturer said, what you read somewhere, whatever. And now one of two things. Either your intuition is not good enough and you're going to learn something new and become better, or you're going to prove that source wrong, and that could be even more fun because you can write a paper about it and tell all the world. And I had examples of both. So if you want, maybe next lecture you'll get to it. Okay, so in that respect, let's take a concrete example. What is the weight of bacteria in your body? Total weight. Let's have a few possible answers. 0.1 kilogram, point few kilograms, say 300 or something. 1 kilogram, few kilograms, or 10 kilograms. Question is clear? Okay, who's voting for 0.1 kilogram? 1, 2, let's make it 3, few. Who's voting for point few? Also 4, 5. Who's voting for 1 kilogram? Seems like the most, if there's something like that. 8 people, 10 people. Who's voting for few kilograms? Okay, another like 8 people. Who's voting for 10 kilograms? Nobody. Okay, so we had the majority voting here, right? Okay, you're going to have some surprises next week. And I would say that the way we got into this, and is really about reading something and like asking ourselves, does it make sense or not? And do a sanity check about it. And from that came, a paper with, I think it was like 6,000 citations. So, good things could happen. Either you learn something new or you can teach the world something new. Have a great week. All the best with the exercise.